Hello everyone. Hope everyone is having a great conference so far. Yeah, I'm going to be talking a bit about calculators, but not only calculators. I'm also going to be going a bit over my personal experience trying to build a calculator and what that entails, especially given my background as sort of a self-proclaimed software guy for many, many years. So in general, I'll go over stuff that I have done in the past that kind of defines the way I am, at least in the software space. Then talk a bit about calculators in general and how I got here, how I got interested in them, and a few interesting things about them. Then I'll go over the design of my own calculator and how that process went from sort of like the ideation process, conception, all the way through finally the manufacture of an actual calculator. So let's get started. Who am I? Here are a few things that characterize what I do. Front and center, you might see a few screenshots from a few games that I have done in the past. So I heavily identify as a game dev, do a lot of graphics, programming, and that kind of thing. I also do pixel art and some artistic endeavors. Some of the art that you see in there is stuff that I have done in the past. To the side, you might see some digital logic and microcontroller stuff. I kind of started in more that digital area and then sort of moved into software because I thought just, man, buying hardware is so expensive. Software, I can at least just code it and I don't need to buy anything more. And you might see the logo with the lambda in there. That's the logo of the Racket language, which is a family of Lisp languages, which I quite enjoy. And recently, yeah, recently I did the Advent of Code last year using Racket. That was pretty good. And to the other side, you have sort of the dark side of the same concepts. You have C and you have Rust, which is sort of my favorite language for systems programming and embedded programming in general. So that would be how I would describe the stuff that I have done basically up until this project, where I started actually going deeper into hardware and designing things and mechanical design, all of that stuff. All right. So let's talk a bit about calculators and the process of doing calculation and I guess how that has evolved over time. Here are a few calculators, OHP. I kind of got into it sort of like when you get power tools, you also always get like one brand. It's kind of the same thing with calculators. You get one HP and then you go, okay, there's a language to this thing and like I want to learn more about this language, I want to continue using this language. Then you get another HP calculator and you sort of just build on forever your family of HP calculators. My favorite one is this HP 35S, the smallest one of that bunch. It's an older calculator compared to the other two, and I quite like the relative simplicity compared to these newer calculators, but HP has a bunch of different concepts, and I think just like as times have progressed, things have just become very bloated. Here is another take on calculators. You have the Curta calculator, which is a mechanical calculator. It's a fascinating device. Basically, all that you can do is addition, and because addition is also subtraction, you can do subtraction, and then because multiplication is a bunch of additions, you can also do multiplication, etc., so on and so forth. And it's a really interesting device. Have never actually held one, but I have seen plenty of people working the inner mechanisms, and it's super interesting. And it's very interesting that you can have such different concepts or executions on sort of like the same initial concept. This is another one that actually looks quite similar to what I ended up designing, and this is from the Clockwork people, and it basically runs on a Raspberry Pi Pico, and it runs a bunch of interesting things. You can run Python on it. It has a full keyboard. It's basically a sort of small computing device that you can do all kinds of computations on. However, the calculator that really got me fascinated and has a really consistent sort of language that you use to interact with it is called the HP 42S. I have only used it in emulators, And that was sufficient to get me hooked into sort of like the philosophy of how it works. And there are a bunch of like very characteristic things that that calculator executes so well. And it executes so well that a different company recently, or somewhat recently, called Swiss Micros, actually built a clone of that calculator that runs the original software via emulation. So that is pretty cool. And the interesting things about that calculator, that sort of like, if you talk to many, many people, they're going to say, this is the best calculator that I think exists. And the reason for that is sort of twofold. You have the experience of using it. Sometimes that's very rewarding. And also this consistent language that you use to interact with the calculator. And all of that sort of makes it very efficient. And because it's a small calculator, that also plays into it. And again, very consistent language. So that calculator sort of inspired me to, okay, what if I had a calculator like that, but I am this guy that likes Lisp languages and Racket, all of this stuff. What if I had a calculator like this, but Lisp? And the sort of functionality that makes this kind of calculator the most known is sort of the reverse Polish notation. Basically, you input whatever you want the operators to be last, and the operands first. So for example, if you want to sum 10 plus 10, you do 10, 10, and then plus. And that's one thing that a lot of people swear by. They say that, oh, this is very efficient. In reality, like, you can get very efficient with other computation models, but it is a very interesting computation model. And I was basically thinking, okay, that's an interesting computation model. Can we translate sort of that into a Lisp kind of thing? And that was the inception of it. I was just thinking, okay, where does this go? And then the first thing that I did is I started thinking about the language of doing things in a calculator. And I got to the fact that you sort of, in many, not only calculators, but in many computational paradigms, you have these three different things. Everyone knows that in programming, naming is one of the fundamental problems that you have to solve. And that's one of the things that any computational platform is going to have to deal with. Also, searching things is another problem. So you have this bunch of different concepts floating around, and you're doing computation with that, and you need a method for assessing all of these things at the same time so you can actually execute on it. And that's search. And finally, I think that's sort of the fundamental thing with computation. Maybe that's what computation is on some definitions. But you can combine all of these different things that you can search and you can name, and you can combine them to create bigger units that have emergent behavior that's more complicated than the individual units that you had initially. So those three things are essentially what you're doing with any calculator. For example, you're doing, oh, I want to do the logarithm of this number. Basically, you're searching for the logarithm, whatever that is, especially when you're interacting with the UI of a calculator. You need to find where that is. And then you're, for example, combining that with the output of a different thing. For example, you want to do 10 times that, then you combine with further things, and at some point you have very complex programs. And on a different aspect, you have these three things that sort of make computation, but also to create a language that people enjoy using, you need to make sure that you're deriving meaning from consistency and reuse. If every time that you want to do something, it's done a different way, it's very hard to keep track of that. But if every time that you want to do something, it's always using the same concepts, then that becomes a language that you can reuse. And to start out with this problem of sort of naming and searching things, when you're working with a calculator form factor, you have a bunch of problems that you don't have with bigger computers. And the first one is the problem with typing out stuff. I think that's the first barrier that you always have with when you are trying to do any kind of more complex computation in a calculator. And the ways that has been solved is the first one, keyboards. Great. I would say that's the most efficient method for typing out stuff. Then At this point, phones are also quite efficient, especially when you compare with other alternative ideas for basically typing out stuff. And phones are efficient because of, I would say, guessing what you want to type. If you just want to use a phone actually typing out and spelling out everything, it's shown that actually your speed decreases significantly. And then I think on a separate category altogether, you have basically everything else that's sort of like resource constrained. And usually the amount of stuff, the amount of information that you can put through this interface is very small. And I think coming back to the HP42S, I think their solution to the typing problem is very interesting. And it's basically this. You have the whole alphabet associated with 6 different keys. And it works as sort of directories. So like if you hit the first key, that's going to expand, and then A, B, C, D, E is going to be shown in each one of the keys. And that means that you can access each one of the letters with basically 2 keystrokes. Of course, that's more than, for example, in the different calculator that I showed, the HP35S, where you have the whole alphabet, every key in a different position, which is similar to like what you have in keyboards. But because you don't use calculators often as you do use keyboards, because you're a sort of a single purpose device, it turns out that getting muscle memory with that is kind of flaky. Maybe like you're doing a project, you use the calculator all the time, and then you get some muscle memory and things are efficient. But you spend a couple months not doing it, suddenly like interacting with the device is much more complicated. So the interesting and nice thing about the 42S, it's a compromise, like you need 2 keystrokes, but it's transparent to basically everyone that picks up a calculator. Okay, this is how I use it. It doesn't require having that sort of muscle memory to get any sort of speed. And it's reasonably efficient. Also, the other interesting thing is because the upper part here would be the screen of the calculator, basically what you're doing is you're labeling buttons to anything that you want while retaining sort of like the physical feedback of hitting a key. And what that allows you is to have menus that also feel very nice to use. For example, you could have a menu for different trigonometric operations using sort of the same concept. And you could even have the same expansion concept in here, like for example, when you hit more, that could display other operations as well. Now, coming back to the Lisp aspect of it, I'll just give a quick primer of how Lisp works, very simple. And then I'll point out some of the things that you can solve in a calculator environment by using Lisp, coupled with a couple interesting editing tricks. So this is roughly how Lisp works. You have these 3 things that you can type out, and they have meanings. So the first one is if you just key mash or like type an actual word, that's basically going to be a table lookup. That's a variable. You have a name that's going to be associated with something. The second one, in the context of a calculator, is you can just type out a number. That's a number, no mystery there. And the third one, and the one that makes Lisp famous, is the function application, which in here is just going to be, for example, sum. And what this means, parentheses, sum 1 through 3, is just apply sum to 1 through 3. So you're going to sum 1 through 3 in this case. Very similar to the equivalent C style function call, which would be sum parentheses 1, 2, 3. And that's basically Lisp. Now, the interesting things that this solves is when you're using a normal calculator, especially if it's not an RPN calculator, it's just your run-of-the-mill calculator, there are 2 problems that you often run into, even if you don't notice, that make the experience of interacting with the device quite frustrating. The first one is inconsistent states. Basically, when you're editing an expression and you have an invalid expression at some point, for example, oh, you open a parenthesis, now you need to make sure you close it in the right spot, but you could close it in the wrong spot, and then the calculator goes, hey, I don't know what you mean. This is just invalid state that you have input here. And the second one is often you enter something first, and you go, okay, that first calculation gave me a result, but now I want to calculate something different but related to the first thing, because my thinking is evolving. I first like, oh, maybe I'm calculating the distance between 2 points, and then I go, okay, but I want to calculate the distance in 3 dimensions. I want to add an extra variable on this thing. So you're editing code a lot more time than you are actually just inputting code that you already know precisely what's going to do. And that happens especially when you're trying to do more complex computations. They are not trivial to keep in mind all the moving parts. Now, one example using Lisp syntax, for example, assuming that first symbol there, the asterisk, is multiplication. One thing that I do very often in my day job is testing radio devices in the field, like actually physically putting radio devices somewhere and doing a bunch of testing and then applying statistics on that. And one of the things that you need while doing that kind of test, very simple thing, is you need to know how long it's going to take you to execute those tests. So for example, if I know that I'm doing a number of iterations of a given test and I know how long each one is going to take, I just multiply those, I get my answer for how long I need to be prepared for. But talking back to like the evolving computation and thinking around things, I might want to change that at some point to say, wait, the test has a duration, but when I set up each one of the tests, there is an overhead on those tests. And I want to track that separately because, for example, I have 2 different kinds of tests or any other reason. So basically, I want to go from this thing to that thing. And now let's see how that would play out if I were editing that as you would usually in a normal calculator. So the initial computation would be duration times iterations. Then my cursor would be at the end because I just typed that. And then I would go, okay, let me move back and let me add a parenthesis there, then move to the start, add another parenthesis, then move to after duration, and let me type plus overhead on that. Of course, you could do this slightly more efficiently, typing out the parentheses right after, but this is the way that you would usually think about doing it, and often the way that you would actually execute that, because you're not often thinking about the utmost efficiency that you could have when typing out in a calculator. Now, as you can see, this demonstrates the problems that I was talking about. First off, at some point here, you have a closed parenthesis, you don't have any open parenthesis. Then, second off, you needed to do a lot of moving around just to change a slight thing that you wanted to add. Now, how that could be solved by using Lisp and the couple editing tricks that I was talking about is like this. So instead of thinking of Lisp as just text, we instead think of Lisp as sequences of lists that can be nested with more lists, and so on and so forth. And in that paradigm, instead of having a cursor, you would have, some people like to call it a hole, where it's just a place that you're going to put something, or it can be a place that already has something, for example. And within that editing paradigm, where like you're not editing text, you're editing Lisp directly, you never touch the text part, you could have an interface that's something like this. So right now you have selected iterations because that's the last thing that you have input. And you want to, similarly to this, you want to transform that to add this plus overhead thing. So what you could do is you could move up, and that would instantly move to duration because you're not editing individual characters of text. It knows that this thing is a variable, that thing is a variable. You can just move one time up, you move to that other variable. You could just hit the plus key, and immediately that would turn, okay, you want to add duration with something else, and you could type overhead, and that's it. You're done. So instead of having all of that moving around, especially moving the cursor around, you just have a couple operations and you can transform the program. Now, another thing that is often overlooked, especially in calculators, is the meaning that's in the order of operations. So for example, if you're summing duration overhead, it doesn't matter what order you're summing those in. But it does matter depending on what framework you have in mind. So for example, depending on how you're thinking, you could think that it makes more sense to have duration plus overhead, or maybe overhead plus duration. And that would communicate something to the reader, right? So in this framework, you could also have a key that you press to signify grab something and then move something in a direction. So you could simply grab overhead and move the whole overhead to switch the order of operations. Of course, this could also be used in more meaningful ways, but the idea here is that you have this sort of editing where like you're not dealing with text, you're dealing with Lisp expressions, but also it's a sort of kinetic kind of editing where you're thinking about the movement and the flow of things, and like you can grab things, but also another thing that you could do in this paradigm is you might want to go from an inner expression to the outer expression. For example, you have a lot of nested expressions, so that could be another verb. Here you'd have the opposite, going from outer to inner. And interestingly, you could also do things like, okay, you have this overhead that you are thinking as, for example, the overhead for each individual test. But maybe actually you want to think of overheads over the whole test. And to do that, you would need to get overhead from inside this inner sum expression to outside of that. So you could have another verb that signifies move things outside of an expression. So you could go grab, overhead, outside, and it would turn into this. And then you could go move the cursor down and plus, and move overhead to inside that expression. Then you could have, for example, iterations plus overhead, or any other thing that you were thinking. But in general, the language for editing without thinking about text directly would be, you can grab things and you can move them up and down, basically, sort of like forward or backwards inside your lists. You can enter nested lists, or you can leave nested lists. And finally, you might want to grab things from to the outside of a list, or grab things and move them to the inside of a list. So that sort of like forms a somewhat concise language that you could use to edit. And because it only has a few actions, it could potentially be easily mapped to a few buttons in a calculator. So that was a lot of the thinking that I had around the language of how you'd interact with this calculator, and sort of like, especially this idea of sort of trying to move things around in a very intuitive way was the main thing that stuck with me, especially when you're going through the process of the physical design of this calculator, which I'm going to now talk about. So most of the actual design of this calculator was done with FreeCAD and KiCad. I tried to use Onshape for some time, and they are, at this point, quite significantly better than FreeCAD. But recently, FreeCAD has been improving a lot, and the latest iterations of this calculator have been fully designed inside FreeCAD. FreeCAD is a program that allows you to do mechanical design and sort of like industrial design and a bunch of other engineering design and computer-aided design. And KiCad allows you to do circuit design for printed circuit boards. Also, on the other side of that, you have the design of things, where you're just thinking around, how am I going to fit everything together? How I want this thing to look? And this is sort of like the first mock-up that I did inside of Inkscape, just thinking, this is how I want this thing to look, but also thinking, okay, how would this implement this sort of Lisp editing language? And you can see there are a bunch of dedicated keys for the important functions around editing. You have big enter and leave keys when you're dealing with nested expressions. Also, on the side, you have this wheel, like a mouse wheel, where you can move up and down. And then on the other side, sort of like as to fit a right-handed person, it would be the grab inside and outside keys. So you can sort of operate the whole calculator with one hand, but it does introduce an interesting thing where like the handedness of the calculator needs to be taught as, oh, we need two separate calculators if you're right or left-handed in some cases, which is an interesting thing on this design process. Here are some of the actual designs. On one side, you have the design of this wheel that you can turn and move things up and down. On the other side, you have a button, and on the bottom there, you have what the shell of the calculator looks like, and that's actually two separate parts, a top and bottom part, and you screw them in together. And now we move on to the part that was the most new to me. I have done some CAD design in the past, and I have done some PCB design in the past, but I had never actually gotten to the manufacturing part. And the reason that I decided here to actually get into that, even though it might be not really cost-effective or really the way that you would usually deal with these things, you might just send them off to be manufactured, is there is a huge learning opportunity just to understand how the whole stack works and how you actually manufacture things. And I think this feeds back up the stack, because if you understand how the manufacturer works, well, you could now design things better to be manufactured. Manufacturing in general is getting a bunch of CAD designs and turning them into actual things that you can see and touch. And there are a plethora of different methods that you can actually use to do that. And every single method that you use has a bunch of different trade-offs on like how quick it is, how efficient it is, how slow it is, and many, many other things. In here, you can also see one of my prototypes of what the calculator looks like. You have the 3 HP calculators, you have my calculator, which now you might understand why it's called Tiny Calc. It's very tiny compared to, I guess, any other calculator that I have seen so far. In terms of manufacturing, the most accessible method is 3D printing at this point. My 3D printer is a 3D printer that I got from JCar for $300, and I have been using it ever since. And I don't understand why people get more expensive 3D printers, because it has been working perfectly so far. 3D printer in general is awesome because it allows you to very, very, very quickly iterate on ideas. I often have days where I have printed upwards to like 10 different versions of something that I'm working on. And that has gone from sometimes even an initial idea to a thing that I'm actually going to manufacture just in that time. But it has a couple drawbacks. The most significant to me in designing a calculator, which is not a very, it doesn't need to deal with high forces or anything. So the most significant one to me is just the resolution that you can get with a 3D printer, which is not that high. They are always evolving, but you also always have stuff like layer lines, and even with resin printers, you also have, when you actually compare that side to side with the other main technology that you can use, which is CNC machining, CNC just has a much higher resolution. But other than that, it's also limited in the choice of materials, both resin and the FDM printers, which are the ones that deposit molten plastic, because the materials need to work with the process. The other common method of manufacturing things is milling and machining, often referred nowadays as CNC, because every milling machine that people actually use or turning machine is actually a CNC machine at this point. And the main issue with CNC in general is it's slow compared to other technologies that we're going to talk about. The good thing about it is very, very, very high resolution. There are some technologies that you can use that get higher resolution, but in terms of like the most accessible ones, that's the one that has the highest resolution. And also the selection of materials is very, very large. You can do things like all kinds of plastics, all the way to all kinds of metals. You can also do, in some cases, ceramics and all kinds of weird stuff. Other than that, you have a couple other manufacturing technologies. They are sort of on the sidelines, but usually prohibitive by cost. One of them is EDM, which is just sort of eroding materials with sparks, roughly speaking. And the other one is injection molding, which usually is coupled with CNC machining because you produce molds and then you inject plastic into those molds. Now, how does one go about actually getting into manufacturing beyond a 3D printer? So the most common like CNC machines are the 3018 machines, which is a broad term for machine size. It's basically 30 centimeters by 18 centimeters. And there are many, many manufacturers that make machines in that size. And the main drawback that you have is because of the size, they have a very low mass. And when you have a very low mass in machines, they're doing essentially drilling to produce a part. You have a lot of vibration, and the range of materials that you can actually use is significantly reduced. Now, one very interesting project in the space, in the space of CNC machines, is the Milo 1.5 and now 2.0 as well, which is a project to produce a fully open hardware CNC machine that's actually capable of doing high quality parts and sort of like has enough weight to absorb those vibrations. I got one of those and I built it in my kitchen, and that's how I sort of got started in actually trying to manufacture things. That was a huge learning experience, but it works and it's an amazing project. Other than that, you also have many, many cheap laser engravers that you can use on many like finishing techniques. Usually the lasers that you can get for cheap are not powerful enough to actually make any parts, actually cut things, but they are powerful enough to engrave things or add detail, add lettering, that kind of thing. Here are some pictures of some interesting processes that I tried. So initially when I got my first 3018 machine, which was very light and not very powerful, and I was trying to actually make calculator shells out of them. The first thing that I got is sort of, not the first, but one of the first that I got was this middle picture there. And that's trying to cut acrylic, which is relatively hard plastic, but it should not be an issue for a CNC machine. But I had lots of trouble because it's a small machine, it can't really deal with those materials. And one way of sidestepping that is through molding. So the core concept behind molding is you usually use a softer material to produce the mold, and then you pour silicone or any other kind of resin that's in liquid form on top of your mold, and then it doesn't matter what your mold is made of because it doesn't require any mechanical strength at that point. You're just pouring a liquid over it, and then the silicone hardens, and you do a second molding process with your silicone output, and now you pour whatever you actually want to make your part out of in the silicone. This is nice because it doesn't really matter how mechanically strong your CNC machine is. You can produce those molds. The only thing that matters is sort of the precision and the surface finish, which is a term for how smooth things look. And you can produce modes. And here on pink, you can see some silicone modes that I made trying to make keycaps for the calculator. And on the other side is sort of like the original mode that I poured silicone over that was produced in the CNC machine. Even though this technique is very promising, dealing with molding is kind of hard. There are multiple different factors that you need to keep in mind. Also, the mold degrades over time, so basically every part that you make, the quality is going to be worse, and at some point you need to remake that mold. So I faced several different issues. In the end, I'm not using this idea right now, but it's a very interesting manufacturing process. And it's especially interesting because there's these things called polyurethanes, which are a kind of plastic, but it is a kind of plastic that you can pour, and it hardens over time. So what you do is you get 2 different bottles of liquid, and to actually harden the plastic, you pour 1 bottle, and then the second one, you mix everything together, and then after whatever amount of time, it actually hardens and becomes just like many other plastics that people actually use to manufacture products. So they basically emulate, for example, ABS, which is a very common kind of plastic. They also emulate basically all kinds of like soft plastics that are used in like tactile stuff. So you can, using sort of like one kind of process, emulate many other different kinds of plastics. The reason that these kinds of things are not used in sort of like large-scale production is because it's slow compared to other techniques, namely injection molding. And here is a picture of when I got the Milo 1.5, and that's me assembling it. The thing on the side on the floor there, that's the spindle. That's essentially the drill that you use to remove material away and produce your part. And this machine can move in sort of like 3 different axes. This table moves sort of forwards and backwards and up and down, and then the stop parts move up and down, and you can sort of like produce 3D parts based on that. And also in the back there, you can see my first CNC machine, the small 3018. And this might look like a shed, but actually this is a cutting-edge machining laboratory. I would say it is the most advanced in Australia. It has all the things that I need to produce parts and iterate in my designs. You can see kind of around here, that's the Milo after several different upgrades, because the thing that they don't tell you is that when you get a CNC machine, the first thing that you want to do is make more parts for this CNC machine to improve itself. And that can go on forever. And here, this is my Ford lathe. This thing was produced in 1954. And still going, still produces amazing parts. Very nice little machine. And there is also a bunch of other stuff in there. I recently made a plasma cutter out of my laser CNC. So always something interesting happening. Here is a photo of my calculator PCB. I'm in the process of soldering this tiny little buttons in there. And an interesting side track that I went into, sort of like in the past couple weeks with this project, is trying to improve the quality of the buttons that I have on this calculator. So injection molding is essentially having some device that you can use to produce molten plastic and then inject that in some kind of mold. And because I'm producing such small parts, I thought I could take a sort of detour into what people usually do with injection machines. Injection machines are usually from $10,000 upwards to like millions of dollars. But because I needed such small parts, I thought all that I need is a metal syringe kind of thing. So I just made something out of a nail and a little cylinder of metal, and I just wrapped wire around that as a heater. And I made my little modes as 3 parts because I essentially needed to produce all of these keycaps, and every one of them has a different inscription on top. So I divided the mode in 3 parts. The middle one is the one that's sort of the key shape, and the top one is the different text that I can swap for. And this is what it looks like. So those are the little modes. And here is a plastic part that I produced in my hyper advanced lab. Yep. I think we don't have time for the demo, but if you guys are interested in looking at it, definitely talk to me after the talk. Yep. Thank you, everyone.